Hi there, good morning, good afternoon, good evening in any part of the world that you may be in today. My name is Alex Chung. I'm a senior product manager in the SageMaker machine learning platform today. I'm joined by Hallie Crosby. I'll let her introduce herself.
Hi, this is Hallie. I'm an AI ML specialist solutions architect, also working on SageMaker.
And today we'll be talking about a very popular topic of leveraging SageMaker for distributed training with Kubeflow pipelines, essentially training at scale for ML ops. And in this webinar or presentation, we'll be covering over a few different things. First is what is SageMaker, the AWS ML platform. Next is ways to adopt SageMaker. And then followed by overview of open source routes to SageMaker in terms of ways that you can integrate SageMaker with open source tools. And then fourth, we'll be talking about scaling ML with SageMaker. And then finally, we will finish with resources to get started and a demo as well in terms of a live presentation with Kubeflow pipelines and distributed training. So to really kick this off, AWS has essentially 3 layers to their ML stack. At the very bottom, it begins with our frameworks. So we take the vanilla open source frameworks from TensorFlow, PyTorch, and MXNet, and then we add in optimizations for AWS. So for example, data loading is significantly faster with our version of the frameworks, and is available from the deep learning containers and also from the deep learning omnis. We also have specialized hardware like elastic inference, and then Inferentia, which is a custom ASIC that allows for the lowest cost of inference on the cloud. And then we have the middle layer, which is our ML platform. So this builds upon the bottom layer, but it leverages SageMaker as really the one-stop shop where you can do anything from data labeling all the way to model inference and hosting. And this is encapsulated as part of the SageMaker branding. And then at the very top, you have the AI services. AI services are essentially tools that oftentimes are built on top of SageMaker, but expose traditional REST-like endpoints that allow you to do very specific actions, such as reading text or translating information or reading out into speech, leveraging machine learning under the hood. These are our AI services. And we'll be focusing today on that middle layer within SageMaker. So one of the things that we've seen quite consistently is the ML lifecycle starts with collecting and preparing training data. So if you're a computer vision based customer, this might be collecting a lot of images and videos. It might then be slicing and dicing it and then getting it labeled. Next, it might be building your custom algorithm. So Amazon SageMaker has first-party algorithms that you can leverage, or you can bring your own. So for example, if you wanted to implement a custom version of mask-RCNN with a modification in terms of the number of layers due to a specific business need, you could do that and package it as part of SageMaker training. So then you essentially could leverage scaled compute to be able to take that container and train on your data sets in large volumes. And you have the flexibility of a lot of extra features like experimentation, model tuning, model debugging, and then also one single panel of glass from SageMaker Studio to view all your different runs and experiments. And then once you have a optimal model that you have found, you can then deploy it into production. You can also implement things like model monitoring. You can also scale out your inference endpoints if you need higher throughput or burst capacity for any specific reason. And then finally, you can do different tools to validate your predictions or take your model and apply offline inference, also known as gang scheduling. And the way you can think about this is the ML ops lifecycle is really the top right, bottom left, 3 quadrants. The top left is really a little bit more than what's traditionally known as data ops, but the top right, and bottom left once again. This is what is being coined as a term ML ops. You'll develop a model in a data science environment. Once you have that model in terms of the model design, number of layers, the tensor design, you'll then save that, commit it into a Git-like environment, and then from there, you'll deploy it into production where it gets retrained on production data and then fed through the entire inferencing process. And the models can be promoted and downgraded in an A/B-like environment. This ML ops term can be summarized in one line as taking models into production for scale. And SageMaker offers a variety of different tools that you can leverage for simplifying your ML ops process. First, we have SageMaker Studio. So SageMaker Studio is a Jupyter lab-like IDE. It allows you to have collaboration at scale. It integrates with other SageMaker features, so you have easy experimentation and management. You can do Autopilot, which is an auto ML generation tool for tabular data. You can also leverage our bells and whistles in terms of additional features that simplify your ability to develop best-in-class models through tools like Debugger, which essentially allows you to snapshot the model tensor state at any given time and inspect it in real time using a sidecar container in SageMaker. And ultimately, these different tools are designed to help you improve productivity. So here's an example of how this looks like. This is a view where there are a number of different training jobs being done, and this is part of SageMaker experiments. We can actually see the different runs that happened, and you compare the different number of epochs relative to the training loss that you have. SageMaker experiments ultimately allows you to have tracking at scale, visualization of your data, metrics and logging, and ultimately it gives you fast iteration capabilities so that you don't necessarily have to save this into either some type of text file or a lightweight database like SQLite in order to track all your different runs and attempts to find the optimal model. SageMaker ultimately is streamlining the ML ops process by offering managed services of each of the different pain points that we've seen. And what this ultimately means is many customers have traditionally tried taking a DIY approach, for example, leveraging a tool like Kubernetes. What we found for many of these customers, setting up Kubernetes is significantly a higher bar without a team that has significant past experience. Proper configuring and auto-scaling of compute is something that has a learning curve as well in terms of proper taints and tolerance, attaching auto-scaling to an EKS cluster. Ultimately, when you're doing auto-scaling, you need to have right sizing of instances for cost efficiency. For example, going back to the idea of taints and tolerance, you don't want any of your CPU-based jobs to sit on a GPU node. Otherwise, you're being billed up to easily 10 to 50x more than what you really needed for your cluster. And also on top of that, SageMaker has all the latest versions of the frameworks regularly updated. So for instance, when PyTorch or TensorFlow releases their latest version, very shortly after, we'll actually package it and release it as part of the SageMaker deep learning containers, which you can build upon to create your machine learning model Docker images. And then ultimately, this becomes a TCO argument where through SageMaker, you can reduce total burden on your ops team. So you can really focus on solving the business problems that help you accelerate your core business and bottom line. And ultimately, another way to look at this is with traditional machine learning of basic classical ML, you might just need one EC2 instance. But the reality is you scale up very quickly, especially as you jump into deep learning. What you can get through SageMaker is via the same command line based interface that you would have with Kubernetes, you can actually get access to a full-fledged managed cluster that is available through SageMaker for all of your different tools that you might need within ML. And what this looks like is you can get the managed service of all your instances, your compute, your OMIs handled for you. You're only billed for when you're using it. That means there's no idle time. It includes a dozen first-party algorithms such as XGBoost, one of the most common algorithms we've seen in machine learning today. It also allows for existing containers to be translated over into SageMaker with fairly minimal modifications. I already touched this, but the DLCs, these deep learning containers, offer MXNet, PyTorch, and TensorFlow available to you where you can just build on top of it. And it's located on all of the SageMaker regions that are currently there, which simplify your load times. There's debugger, there's ground truth data labeling for those with amorphous data sets. And then, of course, we also optimize for cost for customers. And that means you can do things like manage spot training, which will automatically checkpoint your models onto an S3 drive so that if your instance gets recalled and basically terminates, you can automatically start loading on a new instance programmatically through SageMaker. And we see customers interested in leveraging SageMaker with their existing ML environments for several reasons. First, they may have a portability requirement of their application stack. So for instance, if you as a customer of AWS already have Kubernetes investments, you can then continue using your Kubernetes-based tools while still accessing SageMaker. Second, we do see some customers have hybrid cloud mandates. If you're required to use AWS and another cloud provider, you can easily leverage both together. Third, prior technology investments such as DIY ML platforms. So essentially what this means is if you've used Kubernetes as your methodology of portability, you can blend SageMaker as a managed service with your existing tools. So this is very similar to number one. And then finally, when you have on-premise data restrictions, you can leverage SageMaker either for training or for inference. So we see some customers doing SageMaker training and then deploying their models on IoT devices or on-prem. On the flip side, we also see customers doing training on-prem, either on their existing GPU hardware or other specific solutions that they may have created, and then leveraging AWS's pervasive network of regions around the world to do their model inferencing. And we offer customers two routes to access SageMaker from open source tools. The first is Kubeflow Pipelines. So we offer SageMaker Components. For those that are familiar with components, those are the reproducible code that compose an entire pipeline in Kubeflow, these workflows. Second, we offer operators into Kubernetes. Operators are tools in Kubernetes that allow you to apply the specific logic into your underlying cluster. For both of these, rather than executing the code on the local Kubernetes-based cluster, this actually routes the jobs onto SageMaker. So this is the Kubernetes architecture. Most are probably very familiar with this. In most cases, you submit a kubectl, a client for the Kubernetes control plane, where you can submit jobs into Kubernetes and that applies on the cluster. This is oftentimes very challenging and data scientists don't prefer this route. So Kubeflow is another tool that we see many customers using. It provides end-to-end ML workflow orchestration. It has experimentation management, and then also allows you to have easy to create reusable pipelines that can be rerun without any complicated solutions. So this ultimately gets blended with SageMaker, where you take advantage of our SageMaker processing, SageMaker training, batch transforms, so this is gang scheduling, model deployments and updates, so we can create inference endpoints on your behalf, and then also ground truth data labeling. So the way to think about this is you can have Kubeflow Pipelines be your orchestrator, but all of your underlying compute jobs actually run on SageMaker. And this allows you to meld both of these different paradigms together so that you have compute on one side and you have orchestration on another. And this orchestration essentially acts as your centralized platform where both your data scientists and also your ML engineers, this end-to-end cycle known as ML ops, can coexist together. And just to describe this in a slightly different way, for SageMaker Components, this is for Kubeflow Pipelines. This is Kubernetes native. Right now for orchestration, you need to have a self-hosted Kubeflow pipeline environment. We'll share a way to get easily started on Kubeflow Pipelines on AWS later in this presentation. And then your development interface is through Python, which is data science friendly. Your GUI is through Kubeflow Pipeline dashboard to view all of your different jobs. However, you should be using tools like SageMaker Notebooks or SageMaker Studio for development of your models and creating your pipeline, and then ultimately running it and applying it from within the dashboard. And ultimately, this is like a medium level difficulty in terms of usage. SageMaker operators, on the other hand, ultimately are Kubernetes operator custom resources. They basically use the YAML file that are the CRDs, the custom resource definitions. And once again, obviously, it's Kubernetes native. It can be orchestrated by tools like Flight or Argo, which essentially ingest the core YAMLs and then allow you to specify the directed acyclic graph, the DAGs, however you see fit. The dev interface is a YAML, which is more challenging than typical Python for most data scientists. And the GUI is really customized. There's no GUI for Kubernetes today. If you wanted to submit your own jobs through a GUI into a Kubernetes operator, you would need to have your own abstraction layer. And ultimately, that's why we believe that the ease of use for this is generally for an advanced customer. And what I'm trying to reiterate throughout this presentation is SageMaker is closely integrated with open source for orchestration. For all the different phases of model development, data preparation, model training, and model deployment within Kubeflow. So the second, third, and fourth, going from left to right, so data prep through model deployment, is around Kubeflow pipelines. Model development is really the Kubeflow notebooks. SageMaker offers the managed service version of all of these different tools, and it ultimately simplifies and reduces your total cost of ownership in terms of accelerating your company's ability to do ML well. And these tools ultimately still have the entire portability story intact. The containers that you built for Kubernetes can be taken into SageMaker, and vice versa. When you take a container to be ready for SageMaker, you can still pull it out and run it within your Kubernetes-based or container-based environment, as long as you specify the entry point and Docker file properly. Models that are developed in Kubeflow can be easily submitted for SageMaker for managed execution. And simply what that means is using a component, the SageMaker components, or the SageMaker operators, you can use these standardized mechanisms of Kubernetes and Kubeflow pipelines, but ultimately send those jobs into the SageMaker managed experience where you have the universal front end of Kubernetes, but you have the managed backend that significantly reduces your headache in terms of managing all of the underlying infrastructure. And once again, this just reiterates the point that this is fully flexible. When you pick one side of the equation, so managed experience, you don't forego the other. You can have both here. I can move, shift left and right, and ultimately this gives you full flexibility end to end. And the different ways that you can ultimately load your code is through bring your own container. We also have another tool called bring your own script, but specifically bring your own container is probably the more popular for a container-based customer. So essentially what you need to do is you need to package your model code into a container by leveraging a Docker file. You can have actually SageMaker build it for you through bring your own script, or you can just build it for yourself through your CI/CD platform and then have SageMaker ingest it through either Artifactory or through ECR repos. So just to re-summarize, with Kubeflow, you have the benefit of hybrid infrastructure, portability, composability through their Python-based DSL, while at the same time, by integrating this with SageMaker, you have fully managed infrastructure, managed spot training, distributed training, ground truth data labeling, scalable inference endpoints, and all these other bells and whistles. And if you want to get started with SageMaker and open source tools, we have 3 different options. We have the 2 products, the SageMaker components, the SageMaker operators, and we'll be releasing a CloudFormation quick start that allows you to essentially load the Kubeflow pipelines-based environment, optimized to run for accelerated ML compute using SageMaker. And If you already have containers that are being used for ML, you can swap out the base container for where you're loading your framework. So in the Docker file, you would put from TensorFlow, import this repo, and then you would copy your training code into a specific folder structure. And then you would also pass specific environment variables. And this then allows you to use your existing containers into the SageMaker environment. So just to summarize, through SageMaker, you have the benefit of a fully managed service. Companies require sometimes both hybrid on-premise and on the cloud that are oftentimes standardized entirely on Kubernetes. Enterprises may want to adopt an open source ML platform or multi-cloud strategy, which oftentimes, once again, is done via Kubernetes. Or if you're a customer that has existing Kubernetes infrastructure, leveraging AWS and SageMaker through the operators or through the components gives you that full portability while also scaling out your existing solutions with ML tools. These are some links where you can go find more documentation, some blogs and guides, and some workshop information. And now I'm going to hand it over to our star SA, Hallie, for more details on how this actually looks like from an end-to-end demo.
Okay, so now for a demo to give a real life example of what it looks like to implement all the things that Alex has been talking about this far. So this example, we're going to train and deploy a Detectron2 object detection model. So we're going to be using those Amazon SageMaker components to do this. So we'll be using both SageMaker and Kubeflow. This will be a mask RCNN model from the Detectron2 model zoo. It's been trained on a COCO 2017 dataset, and then the training that we're going to do will further fine-tune that model on a custom data set of aerial imagery. So these are drone images. So you're going to be able to detect things from a very high vantage point. And this GitHub link is the link to a code repo that will help you reproduce this code. So just for a brief architecture overview and a high-level overview of what exactly the steps are that I'm going to be doing. So this workflow, it uses Kubeflow Pipelines as the orchestrator and Amazon SageMaker as the backend to run the steps in the workflow. So SageMaker is managing your GPU usage, handling the distributed training. And for the training, we are going to use a custom container. So this is a custom container which is extended from the SageMaker PyTorch 1.5.1 container. So we need to extend that container because we need to build the Detectron2 from sources. So for setup, to use Kubeflow Pipelines, you need an Amazon Elastic Kubernetes service or Amazon EKS cluster and a gateway node to interact with that cluster. A gateway node that I use in this instance will be my local machine. And we'll use that to create an Amazon EKS cluster and access the Kubeflow Pipelines UI. For time's sake, I've already created the Amazon EKS cluster. Also, for the actual running of Kubeflow Pipelines, to create your pipeline, you need to define and compile it. You then deploy it and use it to run workflows. You can define your pipeline in Python and use the Kubeflow Pipelines dashboard, Kubeflow Pipelines CLI, or a Python SDK to compile, deploy, and run your workflows. To run the pipelines, you need to have the data set in an S3 bucket in your account in the same region that you want to deploy this workflow. Also needs to be in the same region where you're running your Amazon SageMaker jobs. For the compile and deploy piece, after defining the pipeline in Python, you have to compile it to an intermediate representation before you can submit it to the Kubeflow Pipeline service. In this case, the intermediate representation is a workflow specification in the form of a YAML file compressed in a tar.gz file. So you will need the KFP or Kubeflow Pipelines SDK to compile your pipeline. So here we have the Notebook Instances tab within Amazon SageMaker. And here I have a MLP3 16x large instance for doing a lot of exploratory data analysis and a lot of that introductory work to get the model fleshed out. So we're just going to open Jupyter Lab. We see that it's in service. And I already have it open here, so I'll just jump to that. This is your typical Jupyter Lab environment, but it's integrated into SageMaker. So I've already done all the work ahead of time to get my model ready, packaged. But some important pieces here to note is what you need to do to make this work with the Kubeflow pipeline. So here we're importing SageMaker, importing Boto3, identifying our session, our account, our role, and then we are going to be logging into Elastic Container Registry with our deep learning containers. So you can see here I'm using US East 2 for both the SageMaker Elastic Container Registry and my private Elastic Container Registry. So we're logging into both because we want to take that pre-existing container that already is in SageMaker and expand it to add those Detectron2 capabilities that we need. So we'll then upload that to our private Elastic Container Registry. You can see that our login succeeded. And then if we move down to this piece, we are going to pragmatize our Docker file, so dockerfile.drone training. So we're going to build this image so that we'll be able to do the distributed training on Amazon SageMaker. We will walk through this file in just a moment. The next step is to build and push. So we're building and pushing that Docker file to the Elastic Container Registry. The next step is to pip install Kubeflow Pipelines, make sure there aren't any upgrades, and then check out which DSL compile that we have. And then finally for the compile piece. So DSL compile, here is my Py file. This is that file that I was talking about earlier that you needed to compile to a tar.gz file for Kubeflow Pipelines. We'll look at that file in just a moment as well. So now we've got this tar file compiled. I downloaded it onto my local computer. Next, we want to upload the pipeline, we want to submit an experiment, and we want to kick off a run. So how do we do that? I've got some little, some commands here already ready to go. But we just need to go into the terminal here. Probably already have them saved to save everyone some time. Yes, so KFP pipeline upload. And then we want to name our pipeline. So here I have D2 drone train deploy webinar, and we'll just call this B, since I already have one instance of it. We have the location of this file, of the tar.gz file, and then we'll just hit enter. That's going to return an important piece of information that we are going to need to submit the Kubeflow pipeline, and that is the ID. So I'm going to go ahead and copy that to my clipboard. Find the next command here. KFP run submit. We have our experiment name, so I'm just going to make sure that that is identical to what I submitted earlier. We have the run name. So I'm just going to make that unique from what I ran earlier. And then, of course, we are going to change this pipeline ID. Oops. To what we copied from the command just a moment ago. Okay. So you can see it's creating the experiment. and the run is submitted. So we have our run ID, our name, status. So now what we want to do is we want to go into the Kubeflow dashboard so that we can see what is going on. So I'm going to get my ML pipeline UI, and then I'm going to forward to port 8080. Now, if we give that just a moment, should be able to go here to localhost 8080, and here we are. So you can see where we named it webinar B. Okay, we can go to this pipeline we created earlier. We can create a run. It's going to pre-populate a lot of the run details. We'll choose the experiment that we also specified earlier. We're running a one-off pipeline instead of a recurring pipeline, and it pulled these parameters in from that tar file. So the region that we're using, we're doing distributed training on MLP316X large. We've got 4 of those. We have our volume size set, our max runtime, endpoint URL. So that's blank right now because both the training and the serving are in the same workflow. So it will pull that in after the training is set. The role ARN, so this is your AIM role, your service role, to make sure you have permissions. Here's our train image that we uploaded to Elastic Container Registry earlier. Yes, we have our location here. We will just make it the same as our run name. Okay, so I'm going to hit start, and you'll see that's going to kick off. And while that's running, I wanted to go through and walk you through these specific files that we had talked about earlier. So let me bring those up. So we have our Docker file. So we're going to go through, open up the Docker file. I'm also going to open up the traindrone.py file. And then last file I want to open up is our py file that we converted to a tar file earlier. Here we are. Okay, so let's start with the Docker file. So we extended one of Amazon SageMaker's existing and predefined SageMaker deep learning framework containers for this demo. So Amazon SageMaker provides pre-built Docker images that include deep learning framework libraries and other dependencies needed for training and inference. So with the Amazon SageMaker Python SDK, you can train and deploy models using these popular deep learning frameworks. These pre-built Docker images are stored in Amazon Elastic Container Registry. The AWS deep learning containers for PyTorch in particular, which is what we're using here, include containers for training on both CPU and GPU, optimized for performance and scale on AWS. So these Docker images have been tested with Amazon SageMaker Elastic Container Registry, EC2, ECS, EKS, and they provide stable versions of NVIDIA CUDA, cuDNN, and Intel MKL, and also other required software components to provide the user a seamless experience for deep learning workloads. All the software components in these images are scanned for security vulnerabilities and updated or patched in accordance with AWS security best practices. So as we did in this example, you can customize these pre-built containers or extend them to handle any additional functional requirements for your algorithm or model that the pre-built Amazon SageMaker Docker image doesn't support. Initially, we have defined our base container. We also have installed the required dependencies for Detectron2. We've also copied our training script and utilities to the container. And then we'll build Detectron2 from source. Line here, we are copying the directory with the training script into the container. We are also defining the environment variable for the directory where the training code will be uploaded. Next, we are defining the training script via a predefined SageMaker variable. So SageMaker will start the training job with these environment variables. Okay, so now to move on to the traindrone.py file. This is our main training script. If we go to line 199 to line 215, down here at the bottom, you can see we have our SageMaker configuration. So essentially what's happening here is argument parsing. So these arguments will be defined by the Kubernetes YAML file. Also, we're using the Detectron2 launch utility to start training on multiple nodes. If we go to this next piece here, launching the D2 distributed training, this is where we start our distributed training job. So again, we're using that Detectron2 launch utility, which in turn, it uses PyTorch native distributed.launch. Also, as a communication backend, we use Nickel as it gives the best performance for GPU-based communication. If we scroll up to line 125, this is where we are defining our training world. So calculating the number of devices in the SageMaker distributed cluster. So these are all parameters of training world. We're using these environmental variables defined by SageMaker to identify things like number of hosts, processes, host rank, and then pass these parameters to Detectron2 launch utility. This is in order to coordinate communication between the different nodes. If we go to line 181 to 193, we can see this is where we're defining our main argument here, our main method for training. So once training is done, we save the model in one of the processes, and the model artifact will be stored in sm_output_model_data.directory. So it's the SageMaker output model directory. It's just the way the environment variable is abbreviated for the SDK. So the content of that directory is automatically uploaded by SageMaker to S3. Also, SageMaker will start training by running the code in the main guard on all the training nodes. So this is what we're referring to here as the main guard. And then you can see here we're making use of the distributed data parallel. Distributed data parallel is a wrapper to implement multiple processing across multiple nodes. So the actual training script will be executed on all processes and all GPU devices. Under the hood, PyTorch distributed data parallel class will ensure coordination of tasks between GPU devices. So distributed data parallel implements data parallelism at the module level, which can run across multiple machines. Applications using distributed data parallel should spawn multiple processes and create a single distributed data parallel instance per process. Distributed data parallel uses collective communications in the torch.distributed package to synchronize gradients and buffers. Specifically, distributed data parallel registers an autograd hook for each parameter given by model.parameters, and the hook will fire when the corresponding gradient is computed in the backward pass. Then distributed data parallel uses that signal to trigger gradient synchronization across the processes. Also, just a note here while we're talking about distributed training, SageMaker distributed training specifically So training heavyweight DNNs such as MaskR, CNN require high per GPU memory, so you can pump one or more high resolution images through the training pipeline. They also require high-speed GPU to GPU interconnect and high-speed networking interconnecting machines, so synchronized all-reduce of gradients can be done efficiently. Amazon SageMaker ML P3 16x large and ML P3 DN 24x large are instance types that meet all of these requirements. So you can get more information on Amazon SageMaker ML instance types in the docs. Also, last file I want to review is the py file where we defined the pipeline. So you've got a couple of imports here from Kubeflow Pipelines. We've specified our name of the bucket. These are just some basic components that you will need to include in your pipeline file as well. And then if you have different components outside of these three, you can add those as well. Those are located in GitHub. So we're defining our training input. We have our input name and then our S3 URI, so our S3 bucket location. We have our training channel specified. So here we have training, my bucket name, which we specified above, and then the semantic drone data set. That's going to point to our training data. As far as defining the deployment, we have our region consistent with everything else in US East 2. We've specified our instance types, MLP316X large, 4 instance count. And you'll notice these things here, these are all inputs that was picked up by when we kicked off the job in Kubeflow earlier. Training image, our train output location, and then here we're pointing to the train channels that we defined above, and then our serving image as well. So here when we define the training component, our region is just going to point to the region above. Same thing here, we have a config file with our hyperparameters. Again, we're pointing to that train channel, our instance type, instance count, everything's been predefined above. Then the next piece is create model. So here we've got training.outputs and then our job name when we create the model name, and then our ML artifact URL. Also, final component here is prediction. So again, create model.output, and for predictions, we're actually only using one instance, and it's the instance type MLG4DN.x large. And again, we are compiling this together. So let me go back to Kubeflow Pipelines and let's see how things are running. Okay, it's still running and we can see that through the logs. So you can see it's starting the training iteration. Another point is if you aren't satisfied with, say, the depth of these logs, which I can't imagine why you wouldn't be, I'll just go to the other slide here. You can go into Amazon SageMaker, go into training jobs, and here you can see our tuning jobs have kicked off, and you can go in and view the logs from here. And so that will take you to CloudWatch console if you want to dive deeper into those logs. Okay, so it looks like our training job completed. Now we are doing creating the model has completed, and now we are deploying the model. So we can go into the input and output. You can see our train channel here. For when we're training the model, it took this from our pipeline definition file and all of our other inputs that we put in there as well. You can see our output parameters, our output artifacts. Same thing for the SageMaker create the model. Let's see, our inputs, outputs, input parameters. It's exactly what we specified in the pipeline file. And so this is going to take a moment to deploy, but we can see here that it is creating our endpoint. You have the endpoint URL. You have different ways to monitor this endpoint. All of this is capabilities of SageMaker. So it's helping you extend reproducibility of your Kubeflow components by using SageMaker to handle all of the compute resources. And you can see earlier, this is an endpoint I did earlier for this example. And you can see it's in service. And some logs here for that as well. Okay, so if you wanted to do this demo on your own, you can go to my GitHub here. This is in collaboration with my colleague, Vadim. So for the specific pieces related to the Kubeflow pipeline definition file, you can open that one here. And you'll see that here. If you want to see the container training file, the main training file, traindrone.py file, that'll take you there. And then the other files you might need are the Docker files. So you can use the main Docker file here, or you can look at the dockerfile.drone training or dockerfile.serving. The rest of this is very good background on, getting that initial training on the COCO 2017 data set. But this is going to be your main file for defining your Kubeflow pipeline definition file. Okay, thank you, and please reach out if you have any questions.